This video will demonstrate some of Flaretot capabilities. It is intended for first-time users, so only covers some of the basics. Flaretot is capable of much more than demonstrated in this video. We will show you how to construct a new Flare network model, as well as import an existing model from Flarenet. Also, how to use the relief load calculations to create network case data for pipe network or relief device sizing. Then, how to set up the network cases to define the Flare network loading for design or rating. Finally, how to size relief valves from the case data already entered for the network. To model a Flare network, the procedure is as follows. If you have an existing Flare network model using Flarenet software, you can import this model directly into Flaretot with a minimum of work. Without an existing model, the network needs to be defined manually as follows. First, you must define the chemical components used in all flow sources. Then, drop network equipment, such as sources, pipes, knockout drums and flares, onto the drawing. Once placed, equipment is connected on screen with the connectors provided. To speed up the process, complicated pipe headers can be created in one step using the Quick Add facility. This creates a header with specified pipe size and material with any number of connections. Tag names are generated automatically from a specified base name. Next, the properties of the network equipment, such as pipes, drums and flares, must be specified by double-clicking on the unit in the drawing. Next, specify flow rates and physical property data for all possible flow cases that may result from each source to the network piping. These cases are usually based on equipment failure or fire, and can be derived from relief load calculations. Finally, network case scenarios are specified as overall combinations of the individual source cases specified previously. For example, a fire case for a particular area would constitute all the fire cases active for sources in that area. First, we show you how to import a Flarenet simulation. Note that importing a simulation will always create a new file, so save any work you have open. You need to export the simulation to a XML file using Flarenet. Then, this XML file can be imported into Flaretot as follows. Using the main menu, click on Import, and then click on Network from Flarenet. Select the XML which you exported. Some versions of Flarenet do not export all network cases in one file, only the active case. Therefore, you can create multiple XML files if required, with different cases, and import these individually, using this dialog. All our cases are in one XML file, so we click on No to finish the import. The import is complete. We now show you how to set up a network manually. Before defining the network, all chemical components used should be specified. The chemical component list is used for the piping network, all modules, such as radiation and dispersion, and all calculations. A new network is created with typical components already added. These can be changed at any time. Click on Setup. Open the Component Manager by clicking on Network Components. The components already selected are displayed in the Component Manager. In our case, octanol is present in the flare compositions, but is not in the default component list. To add octanol, we locate it in the library components. Select one octanol in the library components, and then click on the Add button to add it to our network components. Octanol has been added to the network component list. Now click on OK to save the components. The next step is to create a simple network manually. First, the equipment units are placed on the drawing, and then these are connected. The equipment units that make up the Flare network are selected from the toolbar at the top of the main interface. It is worth noting that if you are only interested in modeling flare radiation, dispersion or noise, and not flare network piping, you only need a simple network without piping. For each flare of interest, only a source and a flare are required. First, we add a piping header with 3 lateral source connections using the Quick Build tool. This tool is located in the Quick Build and Drawing toolbar. We now configure the header arrangement to create in the Quick Build window. Change the number of tailpipes to 3. Change the header base tag name to HDR. Each of the sequential pipes in the header will be given this tag, with a number appended as specified here. In the next step, the location of the header is specified on the drawing. Note that this point corresponds to the red cross on the sketch. Now click on the drawing to locate the header. This point corresponds to the red cross in the previous sketch. If the header extends beyond the drawing size will be increased automatically. Next, the Common Pipe Properties utility opens. Here we specify pipe properties common to the header sections. Note that this utility can be used at any time for any group of pipes. This is a quick way of specifying more than one pipe at a time. Once the Common Pipe class is specified, the remainder of the header pipe section properties can be set. Finally, click on the Apply Changes button to complete the header creation. The new header has been created on the drawing. Now, before adding the remainder of the equipment, we enlarge the view. To do this, click on the Magnify button in the View toolbar. Then, click on the first point of the area to magnify, holding down the mouse button. Then, drag the mouse to the second point and release it. We now place the remainder of the equipment on the drawing. This is selected from the Add toolbox. First, we add a knockout drum, which models removal of liquid as well as pressure drop across the drum. Click on the horizontal knockout drum button. Move to the required position on the drawing and click to place the drum. Now, we add a vertical pipe, which will be the flare stack. Click on the vertical pipe button and place the pipe above the KO drum as before. Note that for both pipes and KO drums, the vertical or horizontal direction refers only to the drawing. Actual arrangement, that is, vertical, horizontal or slope in the case of pipes, is specified in the equipment properties. The drawing orientation can also be changed at any stage in the equipment properties. Now, we add a flare in the same way. Note that there must be at least one flare in a flare network. The flared gas properties are linked into the radiation, dispersion and noise calculation modules. We now connect the equipment units that we have just created. Unused connectors on an equipment unit are shown as crosses, as shown in this example. To connect two units, the connector button is used. The equipment connector changes to green when the connection is allowed. Click to start the connection inlet. Then, move to the knockout drum and complete the connection by clicking on the drum inlet connector. As you can see here, the connection on a vertical pipe defaults to inlet to the top, so the bottom is not allowed as an inlet. Therefore, connect to the top of the symbol for now. We will invert the symbol after connecting. Now, we demonstrate two of the tools used for tidying the drawing. First, we invert the symbol for the pipe to the flare. Select the pipe by clicking on it. Then, click on the X-axis mirror button. The symbol now has the inlet at the bottom. Now, we align the flare stack and flare on the drawing. Select both units by holding down the mouse button at a point above the units, and then drag the mouse to a second point to enclose the units in a selection rectangle. Then release the mouse button. Now the flare and stack are both selected as shown. Finally, click on the vertical align button to align the units. Next, we set the source flow cases and properties for other equipment. The properties for all items on the drawing are accessed by double-clicking on the item in the drawing. We demonstrate with the first source. The first tab contains the description and drawing symbol layout. A tag name must always be provided for all equipment. The orientation section shows a preview of all possible layouts of the symbol, as well as associated text, such as the tag. The current selected layout is highlighted and can be changed by clicking on a new one. The Case Properties tab contains all flows expected from this source. The list of cases is shown in this pane. A minimum of 1 case is required. The data specifying flow rate, physical properties and composition for the case selected in the list is shown here. This data can either be specified or can be linked to a relief load calculation. The data shown in red is required to define the case. Either temperature or liquid fraction can be used to set the stream enthalpy. Chemical composition can be entered in either mole or mass percent, and this can be set as a default for all cases for this source, or specified for each case. Finally, the case type determines the actual pressure for relief device sizing or maximum allowed at the network piping inlet. This pressure is based on the case type and design pressure, as specified in the System Design tab. A case type of none means the pressure given here is the maximum pressure used. To further explain, note that when specifying pressure and temperature, or liquid fraction, this will usually be at normal operating conditions upstream of the relief device. This sets the fluid enthalpy. However, any basis can be used provided the values are consistent. For example, conditions can be specified at relief pressure if known. For either network piping inlet conditions or relief device sizing. The actual pressure for that is used, then conditions are calculated at that pressure, and the same enthalpy as the conditions you specified for the case. Once data has been entered, in this case for the default specified case, the text color changes to blue to indicate data is OK. No further data is required for now. After setting all the source cases, the color changes to blue to indicate they are defined. We set the first tailpipe properties by double-clicking on it. Since the pipe tag is set, and drawing layout does not need changing, we go to the Pipe Properties tab. The piping class must be specified. There are two default classes in a new network. Note that the class is not just the piping material, but also design and manufacturing specifications. These specifications are used to select an appropriate pipe schedule for a given nominal bore. You can also create your own piping classes, including classes with tables of your own allowable custom sizes. We have selected the default carbon steel class. This class is suitable for lower pressure piping using 150-pound flanges, typically used for flare piping. For this class type, nominal bore must be selected. Then pipe schedules available for the nominal bore are shown. These schedules are all those available and not that required by the class. The schedule can be selected manually. We choose Schedule 40 for example. The schedule can also be selected from the pipe class parameters using the Select button. The pipe length must be set. Finally, on the fittings page, outlet fitting must always be specified. This option sets the connection type if connected to a different pipe diameter. If reducer or sharp exit is specified, this will only be modeled if connected to a different size pipe. Outlet fitting type is ignored if connected to a T, as reductions or enlargements are modeled in the T's themselves. Since fitting type is already set at reducer by the Quick Build Header tool, we just click on OK to save the pipe data. After setting the data for the rest of the pipes, these show as defined on the drawing. Note that only length was required for header sections, since other properties were set as a group by the Quick Build Header tool. A quick look at the properties for the knockout drum show no further data is required. We will only model loss over the nozzles, and not the internals. Therefore the default of 0 for design pressure loss is OK. The nozzle sizes are already set automatically from the connected pipes. We now open the flare properties by double-clicking on the flare symbol. The inlet pipe and nozzle diameter are required. These are entered in the flare tip page. The inlet pipe diameter is the same as the flare stack, so use the Set from Inlet Pipe button. Then specify the nozzle diameter. Open the rating page. The pressure loss characteristics for the flare are specified here. We choose the extrapolation from rated curve method, which is recommended. This uses actual flare pressure loss measurements, which are then corrected for density from the test gas to the actual conditions from the piping network. Properties of the test gas used to make the measurements must be specified. Now we enter the test points, comprising pressure loss at various test flow rates. New points are added by clicking on the Add Point button. The data is entered in the grid. Finally, click on OK to save. The network is now defined and ready to solve. Use the Solve Network button to solve the network. The solving progress is shown in the progress dialog. Key parameters can be shown on the drawing by ensuring the property labels are active. To do this, click on View, Property Labels, Show All. More detailed stream information can be viewed in the Property Summary window. The Property Summary displays physical properties for vapor, liquid and water, if present, for all streams. Pipe sizing criteria is also shown at the base of the report. Flare gas properties are now available to run the radiation, dispersion and flare noise calculation modules. In this section, we will show you how to add another case to a source. This new case will be linked to a gas blow-by relief load calculation. This calculation determines relief flow when a liquid control valve fails open on a pressure vessel. This second case will then be used to show how case management is used. Before any relief load calculation can calculate the relief load, the design pressure of the vessel being protected, that is, the source, must be specified. This is because at relief conditions, upstream vessel pressure is based on the allowable overpressure of design. Note that, in this case, this design pressure refers to the vessel downstream of the failed liquid control valve. Double-click on the source to open the Properties dialog. Click on the System Design Page tab. The design pressure is 30 bar gauge, so we enter it here. The Case Properties page contains the specified and relief load cases. To add our new case, linked to the relief load calculation, click on the Add Relief Load Case button. Select a gas blow-by calculation, and then click on OK, which will open the calculation. The data for the gas blow-by calculation is contained in groups. These are opened by clicking on each of the colored headings in the drawing. These are red one undefined and blue ones defined. Note that the design pressure, as previously set, is shown on the drawing. The relief pressure is based on the case type, which is process, and so is 10% overpressure in this case. First, we open the conditions for the vessel upstream of the control valve. The pressure, temperature and composition is required. Note that the specified composition can be that of the vapor, inlet fluid or the liquid in the vessel. However, a flash of this composition at relief pressure must result in some vapor, which forms the basis of the relief load. Invalid data is shown in red and changes to blue once defined. To close and save this data entry, click anywhere on the drawing. Now we specify the control valve by clicking on the label. We first set the tag name. Then, we derive the data for the control valve from the typical control valve database. Data for a 4-inch globe valve with single port and linear characteristics is used. We will allow for a control valve bypass valve being fully open, as well as the control valve failing. You can include a bypass valve by clicking on the checkbox. Then, click on the bypass valve label to enter the valve properties. A generic 2-inch globe valve will be selected. After specifying 2 inches for the nominal bore, the data required is derived from the database, so no further data has to be entered. All required data is now specified so that the relief load can be calculated. Click on the Calculate button. The results are shown in the Calculation Results window. These can be printed or exported from this window. After this window is closed, these results are ready to populate the case data in the source. Close the blow-by calculation and save the results using this button. The case load data has now been populated by the linked relief load calculation. Change the name in the name field to indicate that it is a blow-by case. The name changes in the list automatically. Click on OK to close and save the source data. We are now ready to set up an example network case using this new blow-by source case. Open the Case Manager by clicking on the Case Manager button. The lower grid shows all possible contributing sources to piping network flow. The columns in this grid correspond to the source case index, which is active in a network case. The upper grid shows all the network cases or scenarios. These network cases are typically a plant shutdown, or a fire, or plant power failure, for example. First, we add a new network case, which will comprise blow-by from the first source. That is, only the one new source case will be active. This is only an example, as typically, multiple source cases would be active in a network case. Use the Add Case button to add the network case. Then, rename it to Case 2, Blow-by. Then, set the blow-by case from the first source as active for this network case. To do this, click on the Contributing Elements grid on the first source row and Case to column. Then select the blow-by case. The grid now shows Case 2 is active. The new network case is complete, so close the Case Manager. Select the new blow-by case as the active case by clicking on the Select Case button. You can now see that only flow from the first source is active, as the other sources are grayed out. The network case that is active is shown in the status bar. We run this case by clicking on the Solve button. Now we explore relief valve sizing. We use the first source in the network piping and will size the relief valves based on both source cases, which are already defined. Open the properties of the source by double-clicking on it. Change the source type to Relief Valve. The Relief Valves tab is now visible. Now, open the Case Properties page. Case 1, Design, has a case type of None, and it is a relief valve sizing case. The conditions provided are at normal operation. The None overpressure option, which is the default, implies that the case pressure is already at relief. Clearly the normal operating pressure of 20 bar will not lift the relief valve, since the design pressure is 30 bar gauge. We change the overpressure type to Process, which is equivalent in this case to blocked outlet. The stream pressure will now be set to 10% above design when sizing the relief valve. Move to the Relief Valves tab. The maximum tailpipe outlet pressure, based on all network cases, is required before the relief valves can be calculated. select Balanced Bellows as the relief valve type. Then click on the Size button to size the relief valves. The results window is then displayed. This shows all available relief valves that can be used for the design pressure and service temperature. This also shows sizing calculations for all cases and all selected sizing methods. Finally, configurations which meet required duty are shown. This can include alternative configurations that minimize excess area, if specified. Namely, those with mixed valve sizes, or more than the minimum number required, with a smaller orifice area. After closing the results window, the configuration with smallest excess area, of selected configurations, is set in the installed valves. This is because we have selected the relief valve selection as automatic. You can also select the Use Installed Valves option and specify the actual relief valve installation. Then the calculation will rate the installation instead of sizing it. For example, we will select two valves, one with a P orifice and another with a N, and then rate this installation. First, we change the relief valve selection option to Use Installed Valves. Then we change the valve that is already in the installed valve list. This was added by the previous sizing calculation. Click on the size column for the valve and change it to an N orifice from the list of allowed valves. Then click on the Add Relief Valve button and select P for the orifice size. Now we can rate the installation by using the Calculate button again. The installation is adequate. Close the Source Properties dialog by clicking on OK. Finally, note that the drawing symbol has changed to a relief valve. That completes this brief introduction to Flaretot network piping design, case management and relief valve sizing.